All right, so one of the most important things you learned in Chemistry 101 was how to draw Lewis structures. So I'm going to go through the steps here. We'll do two examples, and you just kind of want to follow along and make sure that you kind of remember this or relearn it. So we'll do two examples. We'll do an example with C2H4 and then sulfate, SO4 2 minus. So the first step in drawing these Lewis structures is that you want to count your valence electrons. And then we remember if we have a negative charge, that means that we gained an electron, so we add an electron. And if you have a positive charge, that means that you lost an electron, so we subtract out an electron. So in order to identify your valence electrons, you want to use a periodic table. I like this one, ptable.com. Remember, everything in group 1 has 1 valence electron, group 2, 2 valence electrons, group 13 or 3A, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then 8 valence electrons. So as we said, carbon here has 4 valence electrons, and we have 2 of them, so that's a total of 8 valence electrons from carbon. Hydrogen only has 1 valence electron, but we have 4 of them, so that's a total of 4 valence electrons from hydrogen for a total of 12 valence electrons for C2H4. In the sulfur component, we have sulfur with its 6 valence electrons. There's only 1 of them, so that's 6 valence electrons from sulfur. Next up, we have oxygen. Oxygen also has 6 valence electrons, but this time we have 4 of them for a total of 24 valence electrons. And then we have a -2 charge. So since it's negative, that means we gained electrons. So that's 2 more valence electrons for a total of 32 valence electrons. After you've counted your valence electrons, the next step is that you want to draw your skeletal structure, but the key here is to do it correctly. So write your skeletal structure. Correctly. And so I'll give you some hints, but some of this is practice. The more you practice, the more you'll see some kind of themes going on and that kind of stuff. So some little hints, hydrogen is always terminal. And then the least electronegative atom, other than hydrogen, goes in the center. Another hint is that OH is a common motif. So you'll see OH quite a bit. And then the last thing is keep it simple. In general, you want to avoid doing crazy shapes, keep everything pretty linear, that kind of thing. So we'll start off with C2H4. Hydrogen has to be terminal, so that means that the carbons have to be in the center. Now, how do you know one carbon is in the center and the other one isn't, or something, some kind of weird, funky shape? It's going to be through practice, practice, practice. So we can know that carbon is going to go in the center, and then we can just place our terminal atoms all around them, right? Making it nice and kind of symmetrical to keep the overall structure relatively simple. You can try other variations where you only have one carbon in the center and then the other carbon kind of terminal. What you'll see is that you'll never be able to get the correct structure. So it's just kind of a practice thing. Then we have SO4, right? Oxygen is up here, sulfur is down here. Top right is more electronegative, so sulfur is the least electronegative, so it goes in the center. And then we're just going to surround it by all the other oxygens because we're going to keep it simple. After we have our skeletal structure drawn, we're going to add electrons. So the first thing you want to start is just with one bond each. And then after that, you want to give atoms octet, starting with the most electronegative atoms. So I'm just going to redraw our skeletal structure down here. And then I'm going to go up and remember that we counted 12 valence electrons. First thing we're going to do is just draw one bond to everything. And then think about how many electrons that's used up. Remember, it's 2 electrons per bond. We have 5 bonds here, so that's 10 electrons. So we have 12 originally minus 10, so we have 2 electrons left. Next thing we're going to do is we're going to give atoms octets, starting with the most electronegative atom. So hydrogen is happy with its duet, so we're not going to worry about that. Then each carbon only has 6 valence electrons. So we're going to go ahead and just give it to one of them. And then after that, we're out of valence electrons, so we can't give the other carbon an octet quite yet. Move on to this sulfate. So again, I'll draw it like this, right? I remember I have 32 valence electrons. I'll draw one bond to everything first. That's 4 bonds or 8 electrons. So that's left with 24 valence electrons. And then I'm going to start giving things octets, starting with the most electronegative atoms. So oxygen is more electronegative here, so it gets the octets. So they each need 6. And 4 times 6 is 24, so that's going to go ahead and use up all my remaining valence electrons. And so we're good to go there in terms of this step. In step 4, we're going to want to move lone pairs to form bonds, specifically double/triple bonds, to achieve 2 main things. The first thing we want to achieve is to give octets. So just some things to remember here. Remember that group 2, period 2, cannot have more than 8 valence electrons. So that's carbon, nitrogen, oxygen, and fluorine, right? They can never have more than 8 valence electrons. Remember that beryllium only wants 4 valence electrons or 2 bonds. Aluminum and boron only want 6 valence electrons or 3 bonds. Remember, hydrogen only wants a duet. And then anything period 3 or below can have more than an octet. So let's redraw our structure up here for our carbon-based compound. And so if we think about octets, this carbon has an octet, right? Has 6 from the bonds, 2 from the lone pairs, that's 8. This carbon is short, right? It only has 6 valence electrons. So we're going to use these lone pair electrons to form a bond to fill it up. Color this in purple, so we'll demonstrate doing this over here. And so we're going to move these lone pairs to form a bond here. And so at that point, we're done, right? Everything has an octet. The two carbons have an octet, so they're happy. And then the hydrogens have an octet, so they're happy. Let's redraw our structure of our sulfur compound on the right. Cool. So we have that structure here. And if we think about it, everything has an octet. So you might think that you're done. Well, you're not actually done because there's a second purpose to moving lone pairs. And that second purpose, so we'll put B here, color this in blue. That second purpose is to minimize formal charge. Formal charge is a very important concept, so it's something you want to be very familiar with. So remember, formal charge is equal to the number of valence electrons on the neutral atoms minus the number of bonds on that atom minus number of electrons in lone pairs. Remember that we want to get the formal charge as low as possible. And then if we do have to have a negative charge, we want to put it on the most electronegative atom. So let's check out the formal charge here on this carbon. So if we think about carbon, it's got 4 valence electrons. And here it has 4 bonds, so 4 minus 4, and then it has no lone pairs, so minus 0 is 0. So the formal charge on the carbon is 0. What about the hydrogen? Let's check it out. They're all the same, right? Hydrogen only has 1 valence electron in its neutral atomic state. Here it has 1 bond and no lone pairs, so it's 0, right? So our formal charge is already 0, so this is as good as this structure is going to get, and that is the correct Lewis structure for C2H4. Let's check out the formal charges over here. So we'll start off with the sulfur. So sulfur normally has 6 valence electrons. Here it has 4 bonds and no lone pairs, so it has a formal charge of +2. +2. That's not good. But let's keep going and see what else we've got. All the oxygens are the same, so we can just look at one of them. Oxygen, just like sulfur, normally has 6 valence electrons. Here it has 1 bond, and then it has 6 lone electrons. Not lone pairs, but lone electrons. So 6 minus 1 minus 6 is -1. So each one of these oxygens have a charge of -1. And so what we kind of notice here is that oxygen needs to lose electrons so it can become more positive, get closer to 0, and sulfur needs to gain. So that way its charge goes closer to 0, right? Becomes more negative. So what we can do here is form double and triple bonds. And so we can move one of these lone pairs over here to form a bond. That'll remove that oxygen's formal charge to 0 and the sulfur's to +1. And then we can do it a second time with a different oxygen. That'll remove that oxygen's formal charge to 0 and this sulfur's formal charge to 0 as well. We don't want to go any further because then the sulfur will have a negative charge and oxygen is more electronegative, so it is what needs to bear the negative charge. So let's see what happens when we draw that. So if you think about the formal charges, go ahead, pause the video, and you can think about the formal charges here, and you'll see that these 2 oxygens have a formal charge of -1, and the sulfur and the other 2 oxygens have a neutral charge. And so this is as good as this structure is going to get, right? We have a -2 overall charge, so that has to come from somewhere. And we have our negative on the most electronegative atom. However, we're still not done yet. We're still not done yet. The last thing we have to do is to check for resonance structures. And so resonance structures are equally correct Lewis structures. So let me just redraw our structure from before. And so if we note here in this top, when we were drawing these double bonds, we chose 2 oxygens to donate those electrons, but we could have just as easily chose either of the other 2 oxygens, right? There was no good reason we chose those 2 oxygens versus the other 2 oxygens. And so what that does when you make this kind of arbitrary choice is it creates equally correct Lewis structures. So we can draw a resonance arrow. That's what this is. Right, where now our double bonds are coming from the other oxygens instead, right? So these are now single bonds. Right, and then the other ones are double bonds. You see both of these structures are equally correct. So some things to remember about resonance structures is it's not that the molecule is flipping back and forth from one to the other. It's that both of these structures are correct, and that the real structure in real life is a superposition of both of them. So in real life, this isn't a single bond and it isn't a double bond, right? It's actually somewhere in between. And so one thing we can do is calculate the BO, the bond order. So when you're calculating the bond order, you want to think about what the average bond is between the Lewis structures. So half the time it's a double bond, the other half of the time it's a single bond. So the bond order is 1.5, right? On average, this is 1.5 bonds. So another way you can calculate bonding orders is you can count the total number of bonds in all the resonance structures. So here we've got 2, here we've got 1, so 2 plus 1. And then you want to divide by how many resonance structures there are. Here's 1, there's 2, right? So that 1 plus 2 is 3, divided by 2 is 1.5. So on average, this oxygen sulfur bond is 1.5. So get familiar with drawing Lewis structures. It is quite a few steps, but it's kind of a fun little puzzle type of thing. And once you get good at it, you get very, very fast at it. But it does take practice, practice, practice.